Welcome to the presentation on chemical bonding. It says, I believe that there are, and then I don't even know how to say this number, protons in the universe and the same number of electrons. It's an estimate by Sir Arthur Eddington. And you also see the chemical compounds of ionic bonds in the nucleus. You know I don't speak Spanish. In English, please. So the learning goals for this presentation are that students understand the type of chemical bonds that form between atoms and understand the properties of the atom that lead to the formation of chemical bonds. So first, we need to look at what's called the octet rule. Atoms tend to be most stable when they have a filled valence shell or a filled orbital valence shell. So for most elements, or for all elements that are less than 36, that means that they follow what's called the octet rule. The reason being, if you have a complete s orbital and a complete p orbital, that together, when you add those up, comes up to a total of 8 valence electrons. If you were to look at the far right side of the periodic table, that would give you the noble gas column would be where you have 8 valence electrons. Now this is only for elements that are less than 36, because once we get bigger than 36 we have to account for the d and the f orbitals. And we're not going to do that at this point. So we're just going to say that the octet rule is where atoms want to be. Now there are a couple of exceptions to the octet rule, even when we're talking about less than 36. Greater than 36 is because of the D and F orbital. But there are exceptions less than 36, and that's with hydrogen and helium. Both of those are stable with only an s orbital. So if they're stable with only an s orbital, that means they only need 2 electrons. You can create what's called a Lewis dot diagram, and a Lewis dot diagram is a way of referencing the valence electron structure of a particular atom or series of atoms. What you do is you draw only the valence electrons. Now the valence electrons represent the electrons that are in the outermost orbital. So if I have a proton, or excuse me, a nucleus, and then around the nucleus I have the various orbitals. For lithium, lithium has 3 electrons. So there's 2 in the inner, or 1 energy orbital, and there's 1 in the outer energy level. So there is only 1 valence electron in lithium, which is drawn right here. You can figure out what the Lewis dot structure is by looking at the columns of the periodic table. Everything in group 1 has 1 valence electron. Group 2, group 3, group 13, group 14, and group 15. Now it keeps going on, group 16, 17, and 18. Now we do skip groups 3 through 12 because those represent the transition elements. Now the Hund's rule is how we figure out how we're going to fill these things. Now this is actually the incorrect representation for carbon, and we'll actually talk about that a little bit later. But this is not energetically correct for carbon. So it says a new element is discovered with the Lewis dot structure of this. What chemical family does it belong to? So if you look, I have 6 total valence electrons. If I have 6 valence electrons, that's going to put me in group 16 of the periodic table, which is on the far right. It's almost close to the noble gases and the halogens. So this is actually called the chalcogens, which is kind of an archaic name for it, or you can refer to it as the group 16. Either one of those would be a correct answer. Now I know it's going to belong there because of its valence electron structure. Now I would need to know more information about its atomic mass or how many energy levels it would be to identify its exact position on the periodic table. Okay, it says the octet rule is really more of a general guideline than a rule. You get the element, the molecule boron trichloride is more stable than boron tetrachloride. Using your knowledge of electron orbitals, speculate on why this is the case. So once again, we're speculating. Okay, we're not going to know the exact answer, but we know that boron initially has 3 valence electrons. Now realize that a chemical bond is formed whenever 2 atoms share electrons between them. Well, if I were to share an electron, I can share an electron and chlorine can share an electron, and that forms a bond. This one can share an electron and chlorine can share an electron, and that would make a bond. Same thing with this one. In order for a 4th bond to form, chlorine would have to contribute 2 electrons to the bonding pair, and that's not stable for either one of the elements. So boron tetrachloride does not tend to be formed because there's no electron for boron to contribute to the bond. The first type of bond we're going to examine is an ionic bond. Ionic bonds can be represented by the Lewis dot structure that you see below. What you see is that sodium initially has 1 valence electron because it's in group 1, and chlorine has 7 valence electrons because it's in group 17. So because of that, this is the initial setup. When the compound sodium chloride is formed, though, the electron is actually removed from the sodium and it goes to the chlorine. So now chlorine has 8 valence electrons where before it had 7, and sodium, depending on how you look at it, either has 0 valence electrons where it once had 1, or you can think of it as having 8 valence electrons. And people say, well, what's the difference between the two? Sodium initially is a proton. It has 2 electrons in its inner orbital. It has 8 electrons. 4, 5, 6, 7, 8. It's got 8 valence electrons, or excuse me, electrons in the next orbital, and then it has a single electron in the outermost, so it only has 1 valence electron. Now, when this 1 electron is removed, this orbital is no longer the valence shell. This is now the valence shell. So since this is the valence shell, there are 8 valence electrons. So in this case, both atoms satisfy the octet rule when an electron is removed from sodium and transferred to chlorine. Okay, whenever you have something that's a positive ion, or a positive that has more protons than it has electrons, it's called a cation. Now, cations tend to be formed in group 1, 2, 3 through 12, and group 13. They are more stable when they have less electrons than they do protons. Example of that is lithium. You see lithium right here. This is the initial atom for lithium. It has 2 inner electrons and then it has 1 outer electrons. That's not stable because it doesn't satisfy the octet rule, and it doesn't satisfy the exceptions to the octet rule. I can remove an electron from lithium and then I satisfied the octet rule. And you say, well, there's not 8 electrons. Yes, but remember, this is an exception to the octet rule. The other option that I could have is I could actually bring in 7 different electrons. And if I bring in 7 different electrons, it would also be stable. But it is more energetically favorable for lithium to lose 1 electron than it is for it to gain 7. It's more likely to occur. So because of that, we can say that lithium tends to form +1 ions. If you have +1 ions, or if you have cations, you need to be able to form anions as well. Now, anions tend to be formed in group 15, 16, and 17, and they are more stable whenever you add electrons or when there are more electrons than there are protons. So once again, you see the example of fluorine that's here. With fluorine, actually these are both drawn wrong. These are both missing 2 electrons, and when you put the 2 electrons there, excuse me, there you go. This is fluorine. Fluorine has, if you look, 7 valence electrons, and that's not stable. Okay, the fluorine ion has 8 valence electrons, and it is more stable because it's completed its orbital shell. Ionic bonds. So what's formed between the 2 ions, a cation and an anion? I have a cation that's positive, and I have an anion that's negative, and those 2 things are attracted to one another by Coulomb's law. Remember, opposites attract. So because there's opposites attract, or because there's a positive and negative charge, this is a very, very strong attraction between the 2. This is a plus whole number charge. So these ionic bonds involve whole number charges. Okay. The reason why we're specifying that is later we'll talk about something called a partial positive or a partial negative charge. So for now, we need to look at it from this perspective. So you have a cation and you have an anion. Now, the ionic bond generally forms between metals and nonmetals. Okay, everything that's in group 13 to the left is considered to be a metal. Everything that's in group 15 to the right tends to be a nonmetal. Now, like we said before, this is an extremely strong bond, and therefore it requires a large amount of energy to break. Not only that, but ionic compounds tend to have very high melting points and very high vaporization points because the amount of energy needed to break or loose or remove something from this ionic bond. Now, it is a highly exothermic reaction, which means that it tends to produce heat whenever you have an ionic bond that's formed. What we have is called the lattice energy, and what happens is you have stacks of cations and anions together, and they tend to form no definite shape. And that's why you tend to see these things, they're brittle because they can easily move from one side to the other. They can just kind of shift. But what the lattice energy is, how much energy it takes to go from a solid crystal structure to a gas. And that's an extremely high amount of energy. So you tend to see these lattice energies tend to be very, very, very large. Now, one thing that you'll see is that the lattice energy actually increases as the charge increases, and that should make a lot of sense. If I have two ions, +1 and -1, they're going to have some sort of attraction between them. But if I were to take the two identical things and just replace it with +2 and -2, the attraction between them is going to be much greater because the charge between them is greater. So the greater the charge, the greater the energy required to remove them from each other. So we know that ionic compounds tend to be solids at room temperature. There are things like table salt, or potassium chloride, or copper sulfate. These things all tend to be solids at room temperature because of the ionization energy, because of the energy required to make them move. They tend to have high melting points and even higher boiling points, and they tend to be very, very brittle. It's not on order or out of order for the melting point of an ionic compound to be somewhere around 3,000 to 4,000 degrees. If you contrast that with something like water that boils at 100 degrees, that's a pretty significant difference. Now, we need to review naming ionic compounds. You're familiar with these. You should know them. You should have already memorized your polyatomic ions and we're ready to go. But the cation is always named first, and then followed by the anion. And you need to make sure that whenever you're writing out the formula, that the charges balance out to 0. Okay. Next, so it says name the ionic compounds below and place them in order of decreasing lattice energy. So the first thing we need to look at is we're going to look at the lattice energy. Barium is a +2 charge. I know that because it's in group 2. Phosphate is a -3 charge. So the first thing that you should realize here is this is not the correct formula for this particular substance. It should be PO4 So now that we have fixed that, we can go ahead and say which one is going to be greater. So we've got a +2 and a -3. We look at the next one. Potassium is in group 1. Sulfate is a -2 charge. And then finally we have +1 and -1. So we can say that these things are actually in order of decreasing lattice energy. Barium phosphate is going to have the greatest lattice energy because it has the greatest charges that are pulling them together. Okay, potassium sulfate is going to have the next greatest lattice energy because it has a higher charge than sodium chloride. So these are actually in the correct order. Now, if I'm going to name these things, this right here is barium because it's the cation, and then I would have to name this would be phosphate. This is potassium because it's the cation, and then the second part is the sulfate molecule. And then finally you have sodium and chloride.